A very good morning to all. Welcome to my second lecture, and I think this is second lecture for this day. This is on roller compacted concrete pavements and interlocking concrete block pavements. Yesterday we had a session on panel concrete pavements and also on self-fill concrete pavements. So again, we have another session on concrete. Now, as I discussed in the last day's class, typically when we talk about concrete pavements, we find the concrete slab resting above the compacted subgrade and the base layers. The base layers can be granular base courses, or in some cases, it can be cementitious subbase and base courses. Now, in the case of a concrete pavement, in the case of a conventional concrete pavement, the concrete slab is the concrete slab dissipates most of the stresses coming onto the pavement surface, whereas the subgrade or the lower layers have got a relatively lesser role when compared to that of the flexible pavements. So a broad classification of concrete pavements can be of what this is demonstrated here. We can have jointed plain cement concrete pavements. Now, as the word suggests, you have finite slabs. You have finite slabs. So where the slabs are connected by means of tie bars across the longitudinal joints, and we may or may not have double bars. Now, the second one is JRCP, jointed reinforced concrete pavement. We don't find these kinds of combinations where we actually provide reinforcement along the length of the pavement. We may not find this in India, but this combination is very common with double bars. Now, another type of concrete pavement, what we can provide is what is referred as CRCP, continuously reinforced concrete pavements, where you find where you do not find transverse joints. You actually find a pavement constructed monolithically. Over a period of time, there is going to be transverse cracks in these pavements. But the reinforcement, which is actually present along the entire length of the pavement, will actually prevent the spalling of these concrete blocks. Now, the next one is Portland cement, or the next one is pre-stressed concrete pavements. This is not a great practice which is being followed in India, but abroad we have actually pre-stressed concrete panel pavements also. Now, our today's discussion is about roller compacted concrete pavements. Now, the keyword what we need to highlight here is this concrete pavement is constructed, or this is compacted by means of a conventional roller. Okay. Now we find the reference of these roller compacted concrete pavement in a couple of IRC documents. You find IRC 68, SP 68, and also you would also find this mention of roller compacted concrete pavement in IRC SP 62. In IRC SP 62, for conventional concrete pavements for low volume roads, you'll actually find a paragraph, section 4.9, for roller compacted concrete pavements. Now, this is also mentioned in the mod specification for low volume roads. Now, although we don't have much of a trials in India to speak about the success of this, we have some limited trials which have been carried out in West Bengal and in Madhya Pradesh, especially in low volume roads. Now, as I told before, the roller compacted concrete pavement gets its name as we are actually using a heavy vibratory steel drum and static rollers to compact this into final form. So if you remember, our conventional concrete pavements, we were either using we need to have proper proper scaffoldings. We used to go for slip form pavers to pave it. But when compared to that, roller compacted concrete pavement, they are placed by means of a conventional asphalt paving, asphalt pavers, and are actually compacted by means of rollers. Now let us have a brief understanding. Let us actually have a brief understanding in which zone or in which zone does roller compacted concrete pavements belong, depending upon the amount of cement content and the amount of water content in the mix. Now, most of you, at least most of you, would have actually implemented what is referred as cement treated base layers or cement treated sub base layers. Now, if you remember the cement content in that, the cement content was relatively less. In the case of sub base layers, you would have been using a cement content of the order of 3 to 4%. In the case of cementitious base layers or cemented base layers, you would have been going for cement contents of the order of say 6 to 7%. Now, if you look at the water content of your cement treated sub base layers and cement treated base layers, you would have been adopted a water content which is actually close to the optimum moisture content of the mixture. So the design of your cementitious or your design of cement treated sub bases, cement treated base layers, or even the stabilization of soil using cement, your water content is basically determined by means of your Proctor test, basically your compaction test. So you determine what is referred as OMC. So if you have got low cement content and low water content, this basically remains in this domain. Now, what happens if my water content is increased? So let us actually talk about say lean concretes. Say for example, let's talk about say dry lean concrete, which is normally provided as a base course in the case of concrete pavements. Now, when you increase the water content slightly more than your water content what you use for your cement treated bases, this becomes more workable, this becomes more flowable mix. It will be having higher slump value, and this is what is referred as your lean concrete. Okay, now you would require scaffoldings for paving, otherwise the workability of this mix is more. It will actually result in the flow of this mixture. So if I increase the water content, this became lean concrete. Now, since more water is available, you will have issues of shrinkage in the case of lean concrete. In comparison with the cement treated base courses where your water content is relatively lesser. Now, suppose you have, so this is domain 1, this is domain 2. Now let us come to domain 3. When you come to domain 3, your cement content is also increased and your water content is also higher. Say your traditional concrete, what you use for say paving operations, this belong to this category. Okay. Now, if I have a lower water content, and a higher cement content, then this belongs to the category of what is referred as roller compacted concrete. So basically, the workability of this mix is very poor. The workability of this mix is in comparison with traditional concrete. In comparison with traditional concrete, this will have a very low slump value. So because it has a very low slump value, the method of compaction what I should adopt should be different. So if I got lower water content and high cement content, this belongs to the category of our roller compacted concrete. So basically, this is the array of different cement stabilized or cement modified mixes depending upon your water content and your cement content.
भाई बड़ा दिक्कत हो गया है, मिल ही नहीं रहा है वो कागज। एक बार सर को फोन लगाना था अपने फोन से।
I request people to mute their mics. Okay. Now, coming to roller compacted concrete gets its name from the heavy vibratory steel drum or rubber tire rollers, which are actually used to compact this into the final form. Okay, so basically the mixed ingredients are same as that of a conventional concrete, but in terms of the composition is different. So let us try to understand how is the composition different. Now, one main thing what we need to understand is the amount of water content in these mixes are low. Since the amount of water content in these mixes are low, you tend to exhibit lower shrinkage when comparison with a conventional concrete. So the occurrence of cracks, the occurrence of shrinkage cracks in the case of roller compacted concrete will actually occur at a wider interval. So we does not require the kind of joints what you normally provide in the case of conventional concrete. Now let us try to understand the different aspects of conventional concrete, and let us actually compare this with roller compacted concrete. Now let us try to understand what are the similarities in these two mixes. So the shared characteristics between these two is basically from the materials perspective. So you have the same material, you will be having coarse aggregates, fine aggregates, you will be having the hydraulic cement binder, you will be having water, and you will be having say admixtures also. So so you can actually find in the case of roller compacted concrete as well as in the case of conventional concrete, in terms of materials, they are the same, and they have similar curing requirements. They have similar curing requirements. Now let us try to see the similarity of roller compacted concrete pavements with asphalt pavement. Now, when you compare this with an asphalt pavement, the aggregate gradation what we have in the case of a roller compacted concrete pavement is a dense graded gradation. Is a dense graded gradation which we normally use in the case of a asphalt mix. And another common similarity is the placement and compaction characteristics of these two mixtures are the same. So you will find conventional asphalt pavers being used for laying RCC pavements, and you will also find the traditional roller compactors, either static or vibratory compactors, that is being used for compacting these mixes. Now, this is what I have written here. The roller compacted concrete pavements has similar strength properties and consist of basic ingredients as that of the conventional concrete, well-graded aggregates, cementitious materials and water, but have different mixed proportions. Now, in comparison with our conventional concrete, RCC has actually got higher percentage of fine aggregates. Now, this will actually allow tighter packing and consolidation. Now, in the case of a conventional concrete, the aggregate gradation plays a less important role when compared to the stiffness of the mastic. Now, in the case of conventional concrete, it is basically the CSH compounds, the calcium silicate hydrate, the CSH compounds which are actually formed. Basically, these are the hydration compounds. They are much predominant in terms of carrying load than the aggregate gradation. But whereas in the case of roller compacted concrete, our aggregate gradation plays a significant role in the load carrying capability of these mixes. Now, when it comes to the amount of water content what we have, the roller compacted concrete pavements should have enough water so as to provide an even distribution of paste, but that water content should not be more. If the water content is more, you will actually have what is known as sinking of these rollers in these mixes. So they should be dry enough to support the weight of rollers after placement, but yet wet enough to ensure an even distribution of paste. Okay. Now, roller compacted concrete pavements can be placed using a conventional asphalt paver with a standard or a high density paver screed, followed by a combination of rollers for its compaction. Now, let us actually compare the aggregate gradations. So this is the aggregate gradation for roller compacted concrete mixes. The black line basically, the black line is basically the envelope. The black line basically represents the envelope for roller compacted concrete pavement, and the light blue line basically represents the aggregate gradation for a dense graded aggregate gradation for asphalt mixes. Now, what we need to understand here is these aggregate gradations will be very close to what is referred as the super pave dense aggregate gradation line, or otherwise what is referred as the 0.45 gradation line. So the gradations which are actually close to the 0.45 gradation line would be denser. So you can actually see when in comparison with an asphalt mix, a roller compacted concrete mixes is actually having similar gradation as that of the asphalt mix. Again, I think this point comes again. This point comes again. Now, the coating of aggregate particles must be achieved in order to obtain a strong and a durable pavement. And in the case of roller compacted concrete pavement, the main key is basically to achieve the required density. So the quality control checks in the case of a roller compacted concrete pavement will be in terms of the relative densities, whatever we are able to achieve under the action of the roller. So one of the small drawback of a roller compacted concrete pavement would be achieving uniform density towards the edge of the pavement. So towards the edge of the pavement, it would be difficult to achieve a compaction level of about 96 to 97%, whereas interior we will be able to achieve. Now, again, in the case of the pattern of rolling, you can actually start the rolling from the edge and proceed to the interior. Now, the main thing is just because we have cement as the binding material, we should actually start our rolling operation before the cement hydration tends to start. Okay, because if the cement hydration tends to start, if you don't compact it before this initiation of hydration process, this would actually result in the formation of hairline cracks. So this is basically a plot between the percentage of strength at maximum density. So with respect to the percentage this is basically a plot between the percentage strength and the relative density. So you can see that there is a significant reduction in strength. There is a significant reduction in strength if we are unable to mobilize sufficient compaction. Now let us actually compare the conventional concrete mixes with the roller compacted concrete mixes in terms of mixed proportions. We'll be having a slightly higher proportion of fine aggregate. This constitutes of well-graded coarse and fine aggregates. This constitutes for nearly 60 to 75% by volume, and the water cement ratio in the case of a conventional concrete pavement would be ranging between 0.4 to 0.45. Whereas in the case of a roller compacted concrete pavement, we are actually having dense well-grade aggregate gradation, which nearly constitutes of about 75 to 85% of the mixture, and the water cement ratio is slightly less when compared to the conventional concrete. In case of workability, your roller compacted concrete pavement is basically a zero slump concrete, but whereas we need sufficient workability in the case of conventional concrete pavement mixes. Now let us try to see the paving equipments. In the case of a conventional concrete, we tend to adopt what is referred as slip form pavers. In the case of say high volume roads, we actually adopt slip form pavers. But whereas in the case of roller compacted concrete mixes, we tend to use what is referred as your asphalt paving mixes. You don't require any foams. This is because this contains lower water content. Now, in terms of hydration, in order to ensure sufficient durability, we should ensure that there is proper hydration of mixture. Now, in terms of curing, thorough curing is required. We require moist curing. We can go for either moist curing or water ponding. Now, in terms of cracking and load transfer, this is one of the major things between a conventional concrete pavement and a roller compacted concrete pavement. in the case of a conventional concrete pavement, as the relative water content in the mixes is higher when compared to RCC pavements, when compared to RCC pavements, there are more likely to have shrinkage cracks. Now, in order to prevent these shrinkage cracks, we are having joints made in the concrete pavement, conventional concrete pavement. So we'll be having joints at every, say, 3.5 or 4.5 meters. This will actually prevent the occurrence of cracks at random locations. But whereas in the case of roller compacted concrete pavement mixes, these joints are not solved, or you don't typically find joints made in the case of roller compacted concrete pavement. This is because this is having lower water content. Mixes having lower water content will tend to have lower shrinkage, and as a result, you may observe shrinkage cracks, but at a wider interval. At a wider intervals of the order of 8 meters, 10 meters, you may find regular cracks. But even if you have regular cracks, just because our gradation is dense aggregate gradation, there would be sufficient interlocking between the two crack portions of the slab. So the joints are not usually sawed. However, sawing will actually prevent the occurrence of random cracks. Now, these are some advantages. We have already discussed this. This is having low paste content. This will actually result in lower shrinkage. Lesser permeability. This is similar to what this is having lesser permeability, and hence you have enhanced durability and resistance to chemical attack. So you find a roller compacted concrete pavement being adopted in loading yards. High flexural strength, and because of that, this can actually support heavy repetitive loading. High compressive strength, high shear strength because you are having dense aggregate gradations. Now, aggregate interlocking. Even if there is a shrinkage crack which is occurring at a regular interval, just because our gradation is a dense gradation, this will tend to have better aggregate interlocking across the joint. Now, we don't require any reinforcements or double bars, and during the construction, we don't require any forms because your mix is zero slump concrete. This can be light colored, so you can even have colored pavements by adding any pigments. Now, this is with respect to the total weight. You can see the cement content utilization in the case of roller compacted concrete pavement is slightly lesser when compared to the conventional concrete. I told conventional concrete pavement, the main strength is mobilized by the hydration compounds of the cement paste. Now, in terms of post-aggregate requirement, the post-aggregate requirement is slightly lesser than when compared to conventional concrete. But whereas you could see your fine aggregate requirement is much higher. This will actually mobilize proper interlocking. Okay, and this is the water content requirement. Now, please note these are in terms of percentage by total weight. Now, this is a cut section view. A comparison between aggregate distribution in the case of conventional PCC and RCC mix. Now, let us try to understand when we could open this for traffic. Now, in the case of a conventional concrete pavement, mix, you can see there are two lines which are being shown. The darker line is basically for a roller compacted concrete paving mix. So you can see once you complete your compaction itself, once you complete the compaction, you are able to mobilize sufficient interlocking. So it basically achieves sufficient strength when compared to a conventional concrete. In the case of a conventional concrete, immediately after placing, the mix will be highly in a plastic stage. Until hydration begins to occur, it hardens and it forms the hydration compounds. Okay, so until the until the saw cutting period. Basically, you do the saw cutting period. Once your initial setting time is over, so until the sawing window is reached or passed, conventional concrete does not have sufficient strength in order to support any occasional light traffic. So you don't allow even lightweight traffic movements in the case of conventional concrete. But whereas in the case of roller compacted concrete pavements, just because your gradation is more denser and you're able to mobilize more interlocking immediately after paving itself, this would be in a position to take light traffic. So this is a major difference. This is a major difference. So, but however, in terms of strength, you don't recommend any traffic movements even for roller compacted concrete pavements and even for PCC until the mixes achieves an adequate strength of nearly 13.8 to 17.2 megapascals. But this is achieved earlier in the case of roller compacted concrete mixes. So these points we have discussed. This is basically a zero slump concrete pavement. Now let us try to understand how do we do a mix design for this. Now the basic mix design in the case of roller compacted concrete mixes is similar to that what we do for our soil aggregate mixes. We perform, say for a selected cement content. For a selected cement content, basically you can choose a trial cement content between the range of say 8 to 12%. Now for a selected cement content, you try to find out what is the optimum moisture content of these mixes. Once you determine the optimum moisture content of these mixes, you have to prepare cube specimens, cylindrical specimens, and even beam specimens for testing different strengths. Now the moisture content of these mixes is basically determined from your Proctor test. But whereas when it comes to the site, you need to do a correction based on the moisture content of the aggregates. So you cannot directly add whatever moisture content that you determine in the laboratory when it comes to the site. So these are the different procedures. We have to choose a well-graded aggregate gradation. Now, if it is in the site, we have to determine the blending proportion. So there are guidelines regarding what is the aggregate gradation you have to follow. You have to see IRC 68 to see what is the aggregate gradation that is being followed. Generally, this is a dense aggregate gradation. A dense aggregate gradation, which is actually close to your 0.45 gradation chart. Now you can select a mid-range cementitious content. So you can select cementitious cement contents in the range of around 8 to 12%. So you can start with say 10%. Now develop moisture density relationship. Once you develop moisture density relationship, you have to prepare specimens and test its strength properties in terms of your conventional cube strength, or if you are in terms of split tensile strength, and also in terms of its flexural strength. Now, once you have identified the cement content, then you can calculate the relative mix proportions. Now, regarding the compaction equipment which you have to use while you do a mix design, there are authors which actually have recommended vibratory compactors for designing the mixes, or otherwise you could go for even a Proctor compactor if this is not available. But worldwide, people tend to use what is referred as a vibratory compactor. You apply vibrations for a specified period. So this is the aggregate gradation. As I told you, this is the 0.45 dense aggregate gradation line. This is the 0.45 dense aggregate gradation line. Now your gradations are dense. That means it is actually close to this line. You have to select a gradation. In the field, you have to determine the blending proportion. Now once you determine this, choose your trial cement content. Once you choose the trial cement content, you will do a typical dry density moisture content relationship by doing a compaction study. So you can either adopt your vibratory hammer for compaction, or you can go for your conventional proctor. So once you determine the moisture content, prepare specimens for determining your compressive strength. See whether your target compressive strength, or suppose your strength is in terms of target flexural strength, see whether at what cement content do you achieve this. So this is basically your RCCP mix design. Now, regarding the water contents that you can start, the water contents may be selected in the range of 4 to 7%. So while you're doing the proctor test, or while you're doing the compaction test, you can go for increments of 1%. Now, the optimum moisture content, which would actually yield the maximum density, shall be established. The exact moisture content in the field shall be established after making field trial constructions. Just like a conventional concrete, we are interested in the strength that is gained by these mixtures at the end of 7th and 28 days. So we have to check whether our target strength properties are achieved. Now, if flexural strength is lower than the desired strength, the trial should be repeated after increasing the cement fly ash, or basically the hydraulic binder content. You have to alter your hydraulic binder content and achieve your desired strength. Now let us come to the pavement design aspect. Now there are two pavement design aspects which I would be discussing in the case of a roller compacted concrete pavement. The first one, which is actually similar to a conventional jointed plain cement concrete pavement. Now this is the recommendation what is given in IRC SP 62, 2014. Now, as I told you, there is a section 4.9. So, IRC SP 62, it actually recommends to consider a roller compacted concrete pavement similar to that of a conventional concrete pavement. But the slab spacing, between the joints is considered of the order of say 6 to 8 meters. So they have actually given a sample calculation. Now this is the sample calculation. Although this thicknesses does not sound to be that logical, they have actually worked out for a design traffic of 100 CVPD, and for a slab which is resting above a subgrade modulus of subgrade reaction of 100 MPa per meter, a thickness of 200 mm is found to be appropriate. Now, the thickness of 200 mm will not be sounding a very good value in the case of low volume roads. Now, this high thickness, you arrive at this high thickness because of two reasons, or because of one main reason. Just because you are following the analysis similar to that of conventional concrete pavement, when you consider the curling stresses, because of daily variation in temperature, and because your slab dimension is about 6 meters, this would actually result in a higher flexural stresses, and this is one of the reason why we are arriving at a thickness of about 200 mm. So this is the design procedure what is suggested in the case of suggested by IRC SP 62. But there are other established design protocols given by the Portland Cement Concrete Association PCCA method. Now, when it comes to Portland Cement Concrete Association method, they do not consider the curling stresses in this. So they are only concerned about two stress level, two conditions. The first thing, the stresses which are arising because of wheel load should not exceed the flexural strength. That is one thing. And the second one is the fatigue damage consideration. So this is sounding to be relatively logical, at least for me. The Portland Cement Concrete Association considers only two criteria for arriving at the slab thickness. One is flexural stresses and fatigue damage. Here, curling stresses are not considered. So, if you do the design as per the PCCA method, this would actually result in slightly in lower thicknesses when compared to IRC SP62. IRC SP62 considers your curling stresses also in the calculation. Now these are the fatigue relationships given. So if you actually look into the PCA fatigue relationship, you can identify the equations of these curves. So basically, this is the 50% curve, considering the best fit based on 50%. Basically, this is the 50% curve by considering that 50% of the points are above and below. This is 95% curve, and this is the design curve. This is a more conservative fatigue design curve. Now, coming to the compaction aspect. So we discussed initially the mixed proportioning. Then we discussed about the design. Then let us talk about the construction aspect. So when it comes to RCCP compaction, this compaction can be carried out using your conventional smooth wheel rollers, either static wheel rollers or by using your vibratory rollers. Now the number of roller passes shall be determined by measuring the in situ density, in the either by using a non-nuclear density gauge or by using a nuclear density gauge. I don't think we permit using nuclear density gauges now, so you can go for a calibrated non-nuclear density gauge for the density relationships. Now, as I told before, it would be difficult to achieve a compaction of nearly 96 to 97%. Now, this is one drawback of this, but irrespective of that, the target compaction density, what has been recommended, is 97%. Now, these are some construction photographs based on the trials which were carried out in Madhya Pradesh. So you can see this is basically a zero-slum concrete, and you can find that this is mixed basically using an Ajax. Of course, when you're using an Ajax, just because your water content is slightly lower when compared to a conventional concrete, you will be having lesser rate of production in terms of dispersing the material from the Ajax to the ground. And you can see a plate vibrator that is being used for doing the initial compaction, and further using static rollers, and this being cured by moist curing. So this is one of the test trial which is carried out in Madhya Pradesh. Again, these are some trials which were carried out in West Bengal for roller compacted concrete pavements. Now let us quickly see what are the limitations of roller compacted concrete pavements. Now, in the case of roller compacted concrete pavements, over a period of time, this actually becomes smooth. Over a period of time, this becomes smooth, and hence this may not be that adequate for a high-speed pavement application, where you find it difficult to mobilize friction. Now, in the case of multiple lifts, just because we have limitations in terms of compacting a 150 mm thick layer as a monolithic layer, we may go for multiple lifts. So when we go for a multiple lifts, the multiple lifts should be placed without much delay to obtain this as a composite section. So this is one very important thing. The multiple lifts should be placed within an hour to ensure good and monolithic pavements. Now, again, regarding the compaction requirement towards the joints, as I mentioned, it would be difficult to achieve higher levels of compaction. So the compaction requirements shall be 96% of the dry density towards the edge, and towards the interior 98% dry density. So this is slightly a higher requirement. Now, in the case of hot weather, you are more likely to have more loss in moisture First of all, our moisture content in RCC is lesser when compared to conventional concrete. So this is of concern in the case of hot weather paving, because this can drastically affect your workability. Okay, now coming to the second topic of discussion. The second topic of discussion for us today is the interlocking concrete block pavements, which is basically covered in IRC SP 63. So if you look at the interlocking concrete block pavements, this is the general cross section of this. Just like similar to any other paving, any other paving operation, this is being constructed on a compacted subgrade. We'll be having the base layer, we will be having the sub base layer, we'll be having the base course. Now above this base course, we'll be having what is referred as a bedding sand. We'll be having what is referred as a bedding sand of nearly 30 plus or minus 5 mm thickness, and over that you will be having your precast interlocking blocks, and the thickness of this interlocking blocks is of the order of 80 to 100 mm. Now, as we discussed in the last session of self-fill concrete pavement, the entire philosophy of interlocking block pavements is basically that we are having shorter slabs. This is in fact a concrete pavement itself, but this we are having shorter slabs, but shorter slabs of such order that we are not developing any flexural stresses in the pavement. Now, the behavior of interlocking block pavements is very different when you compare with that of a conventional concrete. This behaves as a flexible unit. So this is the load transfer or the load carrying is not basically based on your slab action as you find in the case of conventional concrete pavements. Now these are so as I told you, this has been covered in IRC SP 63. Now these are the typical block thicknesses that we normally adopt. For light traffic, the thickness of the block can be of 60 mm. Now for medium traffic, so basically this guideline has clearly given what should be the thicknesses of the blocks that we should be going for. The thickness of the block in the case of medium traffic, so it has actually defined what is medium traffic. For traffic less than 10 MSA, we can go for blocks having thickness of 60 to 80 mm. And for heavy traffic, where your traffic volumes are of the order of 10 to 20 MSA, especially in town areas, you should actually go for thicker blocks of the order of 100 to 120 mm. Now, as I told you, this is going to behave like a flexible pavement. The success of this interlocking block pavement is basically that you should have a stronger foundation. You should have stronger foundation, well compacted foundation. Okay, so the success of this interlocking block pavements is basically suitable foundation, adequate joint gap. This is very important because if we don't provide adequate joint gap, it would be very difficult for us to intrude our filling sand. This is one thing. So you will have poor load transfer from one block to another. And the gradation, what you follow for the bedding sand is very important, because bedding sand is expected to mobilize some amount of interlocking, and the jointing sand is also the jointing sand, which is basically we place along two blocks. This is also important because when a V load comes here, it is expected that the neighboring block also participates in the load carrying. So if the neighboring block does not take part in the load carrying, what happens is these blocks will differentially settle. Okay, so in order to prevent this differential settlement, it is very important that the gradation of the bedding sand and the gradation of the joint filler sand, whatever you're adopting, is appropriate. So basically IRC SP 63 provides guidelines on how these gradations have to be chosen. Now these are different blocks of these are different shapes what is available. So there are 4 types that has been mentioned in IRC SP 63. The first one is similar to that of a paving brick, and the second one is a dentated shape which will actually provide more interlocking, and the third one is basically the L-shaped blocks which will actually permit a slightly faster paving. Now this is the X-shaped block which will actually provide better interlocking and faster paving. Now I kindly request people to mute their mics. Okay, now coming to the laying pattern, there are several laying patterns which have been identified in the code. So possibly you would be aware of these laying patterns. These are the conventional structure or running bonds. The most common one what people tend to adopt is the herringbone laying pattern. Now there are different categories. Now this has become very common that we find even people using in referential areas also. And even if you look at this referential areas, if you look at some of these interlocking concrete blocks, in order to make this interlocking concrete blocks more fancy, different varieties of shapes are also available in the market. But some of these shapes would actually result in taking bending stresses to these blocks, and as a result you will find these blocks undergoing cracking. So you should be careful while you select the paving block shape. Now the need for jointing sand. So as I told you, if we don't have sufficient jointing sand properly placed, there can be a rotation at these joints. There can be excessive stresses coming at these joints, and as a result, there are chances of possible cracks. And suppose if there is not sufficient jointing sand here, and if the wheel is placed on this particular block, there will not be load transfer from one block to another. As a result, you are likely to see a differential settlement also. Now regarding the laying pattern, especially on curves, you will find people adopting different laying pattern. So you can see up to here they have been adopting a stretcher bond pattern, and you would be finding a herringbone pattern when it comes to the curved areas. Now let us also see the effect of edge restraint. Now this is very important. Edge restraints are very important. Now the problem, one of the major issues what I have observed when people construct this interlocking block pavements is that they tend to construct the block pavements initially, and on a later time only you will find them placing these curb stones or this edge restraint. Now when compared to that, if you're actually placing your edge strips or your curb stones initially and doing a paving operation or doing a placing of these interlocking concrete blocks, you are likely to get better confinement. So in most of the cases, what I have found is people would be placing these blocks and later only these edge restraints are being made. But in that scenario, this will actually result in poor confinement when compared to the right procedure of placing these curb stones initially. And we have to ensure that these curb stones are actually having a flat face near the block area. This will actually give more levels of confinement. And regarding this sand bed, whenever we are placing this sand bed above this compacted base courses, the construction of the lower layers is just similar to any other flexible pavement. You have to achieve the required densities. Now, when it comes to the bedding sand, these bedding sand, you need to do a compaction of this bedding sand at a sufficient water content, which is identified as optimum water content for this sand. and you have to ensure that the bedding sand, whatever you procure, have to be covered with some cover. Otherwise, the rate of evaporation from this bedding sand is going to be larger, and you will be finding difficulty in compacting this bedding sand. Basically, sand is difficult to compact. Sand is difficult to compact. So, in the absence of water, you will find it more difficult to compact. This would actually result in over a period of time, as Warangal starts moving, you will actually find differential settlement if you don't properly compact your sand bed. Now, let me discuss with you some of the earlier research studies which were actually carried out for paving blocks. Now, majority, if you look at any new technology that has been attempted in the roads, we find that there would have been any pilot study in the laboratory, or in the form of any small test track studies. So I'm actually presenting one of the plate load test studies which were carried out in IIT Kharagpur in 2002. This is basically done by the research scholars in the structure of division. So you can find they were doing a tank study. They were doing a tank study. So you can find the loading frame here. This is the loading frame. Okay, and you can find a hydraulic jack kind of a system for applying the static load. So this is the tank. This one is a tank. Okay, this one is a tank, and you can find the lower layers being placed. Okay, so you can find a granular sub-base force which is compacted to the required density. On the top of that, they were actually placing bedding sand. Now, on the bedding sand, they were having concrete blocks, and these bedding sand and the filler sand. The filler sand is basically between two blocks. The bedding sand and the filler sand were basically selected from different fine aggregate gradations given in the BIS code. So different zones of fine aggregate gradations were experimented, and the angle of shearing resistance of these filler sands were basically evaluated by doing a box shear test. So you can see zone 1 sand material actually have a relatively higher phi value when compared to the other sands. So these are the sand gradations which has been recommended. Now, so this is a loading. A hydraulic jack was used to apply a static loading of 51 kilonewtons on a rigid circular plate of about 300 mm diameter. So this is your conventional plate load test. So using the jack, they were pumping oil. And they were applying this load. And they actually experimented this for different parameters, for different variables, such as what you refer as the joint width. Okay, now joint width basically refers to the spacing between these two blocks. Then thickness of the bedding sand, this thickness of the bedding sand, and the quality of bedding sand. In terms of quality of bedding sand, they were varying the aggregate gradation, and they also tried combination where with and without edge restraint. Now the results from this test is very important, so as to understand what would really happen in the field. Now, in order to simulate this with and without edge restraint, what that it is, you could actually find that there is actually filling sand between the rear block and the wall of the tank. So here there is filler sand. So they simulated two condition. With edge restraint, they actually placed the filler sand, and in order to simulate the without edge restraint, they removed the filler sand. So there is a vacant space here. So that simulated the without edge restraint condition. So when we translate these conditions to the field, these are the likely scenarios that we are likely to get. in places where we don't provide adequate join width, in places where we provide higher join width, in places where we have excessive thickness of bedding sand, or you are not able to compact your bedding sand to proper level. So those were the variables. Those were the variables that they try to simulate in the lab. And the parameter what they were trying to measure out of after simulating all these combinations was basically the deflection of the plate. So they apply certain test conditions, they simulate certain test conditions, and they used to and they keep this plate, apply loading. Now they observe the deflection, the deflection of the deflection of this block. Basically, it undergoes deflection. It undergoes deflection. So they were trying to measure the deflection. So let us try to see the results. So they tried for different joint spacings. Okay. Now when they tried for different joint spacing, along with different joint spacing, they also simulated two conditions: with restraint, without restraint. So with restraint, as I mentioned to you, it was a condition where they were having filling sand at this edge. So you can actually see in the absence of edge restraint, they were actually getting higher center deflection. They were getting higher center deflection in the absence of the edge restraint. Now, when restraint was provided, the deflection values were lower. Okay. Now, again, when the joint spacing was increased, for example, for about 4 mm, the deflection values were reduced. Now, this was because of the reason that between the blocks, when they increased the joint spacing, they were able to have a larger incorporation of jointing sand. Now, the second scenario is when they tried, so this was the first scenario. The second scenario is where when they varied the gradation of the jointing sand. So you can see these were the jointing sands. What they tried. They tried different jointing sands. Okay, for different jointing sands, these are the deflections that were observed for different joint width. So you can find the jointing sand as per zone 1 was found to have lower deflection, and hence they recommended this jointing sand for interlocking concrete block pavements. Now this is the case when your joint width as well as the gradation of the bedding sand was also varied, and this was the case where the thickness of the bedding sand was varied. So you could see here there is an optimum bedding sand thickness. Because if you tend to provide a higher bedding sand thickness of the order of 60 mm, 80 mm, as I told you, these are sand. You will actually find difficulty in compacting sand if you're actually going for thicker layers. So there is an optimum thickness of the bedding sand beyond which, if you try to provide, you will be finding difficulty in compaction. So based on the lessons what they learned, and based on the studies what so this is one of the major studies which was carried out in India, laboratory studies which was carried out in India in IIT Kharagpur for interlocking block pavements. Now, based on the study carried out by several other researchers, there are several people who even carried out accelerated pavement testing facility, where they constructed small test tracks, and they were trying to see how different parameters such as deformation or deflections, they were trying to quantify this after certain wheel passes. So based on the experiences gained from several researchers, this code IRC SP63 was revised in 2014, and they actually proposed different pavement thicknesses, different block thicknesses for different traffic levels. So you can see for a pedestrian facility or for a cycle track facility, this is the thicknesses of the blocks which is recommended, and you can actually see this is actually provided for two subgrade conditions: strong subgrades and for weak subgrades. And in the case of traffic level less than 10 MSA, you can find that the blocks are the thickness of the blocks are increased. When the traffic volumes are increased of the order of 10 to 20 MSA, again you can find the block thicknesses are increased. And when the traffic volume is again increased up to 20 to 50 MSA, this is the block thicknesses what is been recommended. And you can see the recommendations for thickness of the lower layers also, And another important fact is the grade of concrete. The grade of concrete what has been recommended for these blocks, this also plays a major role. Otherwise, because each of these blocks are actually subjected to excessive compressive stresses, so the grade of concrete is also important. Now, based on the study conducted by several researchers, our IRC SP63 recommends these two gradations. So you could actually see there were several gradations that was studied that were studied by Panda and Ashok in 2002. There were several bedding sand and jointing sand gradations which were studied. So in IRC SP63, you will find bedding sand gradations and joint filling sand gradations, which has been recommended by the code. Now it is quite difficult. Say one of the major issue what we find in the case of implementation side is people generally tend to ignore all these gradations. As a result, you are likely to encounter situations where your bedding sand is not compacted properly. So if it is not compacted properly, if you observe many of your interlocking block pavements which has failed prematurely, you will observe differential settlement. You will see differential settlement, and also you will also see in the cases where you are unable to provide sufficient joint filling sand between the space. Again, one of the other checks what we need to look into, in the case of interlocking concrete block pavements is the case where we are actually getting blocks of different thicknesses. Again, this is of great concern. On a random basis, it is very important that we should actually check for the thicknesses of these blocks. We need to collect these blocks in a random manner, and you have to test for its thicknesses using a length gauge, or you should also send it to accredited labs to check its compressive strength. So non-uniform thicknesses of the blocks will affect the evenness of the surface, and the maximum allowable tolerance what is given by the code is plus or minus 2 mm. Now coming to the construction aspect. So here also we discussed about the design aspect. We discussed about the composition aspect. Now the composition aspect here, basically your concrete blocks is basically provided by the manufacturer. So we are actually concerned about the strength of concrete. Now the other material aspects in the case of your interlocking block pavements is your gradation of your bedding sand and your filling sand. Now coming to the construction side, the construction is similar to the construction of any other flexible pavement. So you need to compact the subgrade, subbase, and the base. The success of an interlocking block pavement depends upon how well you are compacting your lower layers. You need to have a firm, non-erodable base for the success of a interlocking block pavement. Now, bedding sand of defined thickness, you should actually have a loose bedding sand thickness of the order of 25 to 50 mm, and this has to be compacted by using a plate vibrators to the required thickness. Now this thickness is what I'm providing is about 20 to 25 mm, but based on the design thickness requirement, you have to compact and achieve the desired density. So you can use either plate vibrators. Your construction is mainly a manual operation, so you need to use plate vibrators, or you can use vibratory compactors, so that you are able to you are able to speed up the work. Now, edge restraint, this is one of the major things. Edge restraint should be established before laying the blocks. Now, once the blocks are laid, the blocks should not be tightly laid. Okay, if the blocks are tightly laid, you will find a difficulty in filling your jointing sand. So basically, you spread the jointing sand, and you tend to fill these by brooms. So it would be difficult if you're trying to keep these blocks in a very tight way. So once these interlocking blocks are also placed, you would find vibratory roller passes, in order to firmly place the blocks in the bedding sand. Now, these are some of the common failures what has been observed in an interlocking concrete block pavements. Now, the drainage condition of the lower layers, or the drainage condition of the pavement, is very important in the case of the success of this interlocking block pavements. Now, suppose if you are actually providing in a condition where you don't where your neighboring land, say where your neighboring land surface, as what you could see in this figure, your neighboring land and your pavement surface is at the same level. So the question is, you're not providing a cross drainage structure here. The question is, where do the water that is entering inside the interlocking block pavement structure, where is it supposed to go? So even though you have provided granular subbase cores, this would actually entertain water from your neighboring land also, because when compared to soil, your granular layers are having more permeability. So water will not be sitting in the neighboring land; it will tend to prefer to come into the pavement. So ultimately, if your drainage of the lower layers is not properly established, even if you provide an interlocking block pavement, your interlocking block pavement are gonna fail there. So this is not only in the case of interlocking block pavements. The success of any of your roads, whether you are going for a flexible pavement surface, the success of any of these roads belongs or basically depends upon how well your subsurface drainage and your cross surface drainage is provided. So if you don't provide it properly, your subgrade becomes soft. As a subgrade becomes soft, and moreover, in the case of interlocking block pavements, you may find the pumping of your fine particles out, and as a result, you will find differential settlement. So this is one of the very common failures what people see. The second kind of failure is basically differential settlement, where when you don't provide sufficient jointing sand, these blocks will try to take this process individually, and you will have excessive punching shear stresses, and this is gonna result in failure. And suppose your edge restraints are not properly built, you will find settlement issues. So these are the common failures what people are likely to encounter. So the success, or how to correct this is, the main advantage in the case of an interlocking block pavement is that you could remove these blocks. And then do a recompaction. But however, you should whenever you are planning an interlocking block pavement, or any pavement structure as a whole, you should provide sufficient subsurface drainage and as well as cross surface drainage facilities. This is the success of any pavement. Now, I have just compiled the advantages and limitations of interlocking concrete block pavements. Interlocking concrete block pavements does not require curing, unlike other concrete pavements. Say all the other three concrete pavements what we discussed previously. Say for example, the first one what we discussed was short panel concrete pavement, or say self-fill concrete pavement, or say the roller compacted concrete pavement. All of them require a curing period. So you cannot open the road to traffic. So here, in the case of interlocking concrete block pavement, you could open the road to traffic immediately after construction. Now, this requires less sophisticated equipments, when compared to say pavers or any compaction equipments, very precise compaction equipments. You don't require these sophisticated equipments. However, this is labor intensive. And this system provides ready access to underground utility. Now, this is one of the major issue what we face in the case of our any of our pavements, whether it is low volume or high volume roads. You find people coming and digging for restoring the pipe facilities or restoring the telecom or electric facilities. Now, low maintenance cost and a high salvage value ensures a low life cycle cost. Basically, you could, if at all you find any settlement issues, you could remove these blocks, do a compaction, restore it back. So low maintenance cost and a high salvage value ensures a low life cycle cost for this technology. Now, the limitation is that we need to ensure the quality control of these blocks in the factory premises. Now, you will find that there are several people who come into the sector selling interlocking concrete block pavements. So quality control of these blocks is a very important aspect what you need to look into, because these blocks are subjected to excessive compressive stresses. So this is very important. Now, any deviation in the base course will be reflected on the surface. So as I mentioned continuously, your success of this block pavement depends upon on establishing a non-erodible base. Now, the third one is you should ensure high quality and gradation of bedding sand and joint filler sand, which are essential for good performance. Poor drainage of the lower layers can lead to faster deterioration, and this is not generally recommended for high-speed roads. Say once you actually have your jointing sand getting eroded away, there are chances of rotation at these joints. So this will actually cause disturbance in the case of high-speed roads. So this is one of the limitation of interlocking concrete block pavements. So thank you. So we have discussed two more new